Artificial intelligence is entering a new era. Instead of a single AI system working alone, multiple AI agents are beginning to collaborate, each taking on specialized roles to solve complex problems together. However, as the number of AI agents increases, so do new challenges, deadlocks, resource conflicts, duplicate execution, cascading failures, and unclear responsibility. In this video, we'll explore AI coordination engineering, a new engineering discipline that applies the principles of software engineering and distributed systems to build reliable, trustworthy, and scalable multi-agent systems. Let's discover how coordinated AI can become the foundation of the next generation of intelligent systems. AI agents are rapidly becoming a fundamental part of modern software systems. Today, we already see specialized agents designed for different roles. Research agents gather information. Coding agents generate software. Planning agents organize complex tasks. Review agents evaluate quality. And execution agents carry out actions in the real world. Each agent excels at a specific capability, but real-world problems are too complex for any single agent to solve alone. As organizations adopt multiple AI agents, the real challenge is no longer building individual agents, it is enabling them to work together effectively. In other words, the future of AI depends not only on intelligent agents, but on intelligent coordination. Artificial intelligence alone is not enough. A highly capable AI agent can solve individual tasks, but real-world work rarely depends on a single agent. Complex problems require research, planning, implementation, review, and execution to happen together. The true value of AI emerges when these specialized agents collaborate toward a shared objective. Coordination allows each agent to contribute its strengths, exchange information, and make decisions based on the work of others. Without coordination, even highly intelligent agents can produce duplicated work, conflicting actions, or inconsistent results. As AI systems become larger and more distributed, coordination is becoming just as important as intelligence itself. That is why the next frontier of AI is not simply building smarter agents, it is building reliable systems that enable many agents to work together effectively. Artificial intelligence is becoming increasingly collaborative. Instead of relying on a single AI system, organizations are now connecting multiple specialized AI agents, external tools, and structured workflows to solve complex problems together. The process begins with humans. People define the goals, provide direction, and decide what needs to be accomplished. Next, specialized AI agents divide the work. One agent may conduct research, another may generate code, while others review results or plan the next steps. To perform these tasks, the agents use external tools such as databases, APIs, and software services to gather information and interact with the outside world. Their activities are then coordinated through workflows that determine the order of execution, manage dependencies, and automate the overall process. Finally, all of these components work together to support the organization, improving operational efficiency, enabling better decision-making, and creating greater business value. In other words, AI collaboration is not simply about connecting multiple AI agents. It is about integrating humans, AI, tools, workflows, and organizations into a single coordinated system. Many of the challenges we face in AI collaboration are not entirely new. For decades, distributed systems have addressed the problem of coordinating multiple computers and services to work together reliably. They introduced principles such as synchronization, fault tolerance, scalability, and consistency, enabling large-scale systems like cloud platforms and the Internet to operate successfully. These ideas were later adopted by software engineering, where they became the foundation for building reliable, maintainable, and scalable applications. The same thinking was then applied to workflow systems, allowing organizations to coordinate complex business processes through structured tasks, automation, and process management. Today, we are entering the next stage. Instead of coordinating only computers or business processes, we must coordinate multiple AI agents that collaborate, share information, and make decisions together. In other words, AI collaboration is not an isolated discipline. It is the natural evolution of distributed systems, software engineering, and workflow management, applied to the age of intelligent agents. By learning from these established engineering disciplines, we can build AI systems that are not only intelligent, but also reliable, scalable, and capable of working together effectively. As organizations adopt multiple AI agents, collaboration becomes more powerful, but also more complex. When many agents, people, and tools work together, failures often occur not because the AI is unintelligent, but because the coordination itself breaks down. There are 5 common coordination failures that appear repeatedly in distributed systems, software engineering, and now in multi-agent AI. The first is deadlock, where agents wait for one another and no progress can be made. The second is race condition, where multiple agents compete for the same resource at the same time, producing inconsistent or conflicting results. The third is duplicate execution, where identical tasks are performed repeatedly, wasting time, computational resources, and AI tokens. The fourth is cascading failure, where a mistake or delay in one component spreads throughout the entire system, causing larger disruptions. And finally, responsibility diffusion, where no one clearly owns a decision or action, resulting in delayed responses and unresolved problems. These 5 patterns are well known in software engineering, but they are becoming equally important in the era of AI collaboration. Understanding these coordination failures is the first step toward building reliable, scalable, and trustworthy multi-agent systems. One of the most fundamental coordination failures is deadlock. A deadlock occurs when 2 or more agents each hold a resource that another agent needs, and everyone continues waiting. As a result, no one can move forward. In this example, Agent A is holding resource 1 while waiting for resource 2. At the same time, Agent B is holding resource 2 while waiting for resource 1. Because neither agent is willing, or able, to release its resource first, both remain blocked indefinitely. This creates a circular dependency where every participant is waiting for someone else to act, causing the entire workflow to stop. Deadlocks are well known in distributed systems and database management, but they are becoming increasingly common in multi-agent AI systems as agents coordinate tasks and share resources. Without mechanisms to detect and resolve deadlocks, an entire AI workflow can become permanently stalled, even though every individual agent is functioning correctly. In other words, the problem is not the intelligence of the agents, it is the lack of coordination between them. Deadlocks are a common coordination problem, but they can be prevented and resolved through well-established engineering techniques. The first approach is timeout. If an agent waits too long for a resource, it stops waiting, releases what it holds if necessary, and retries later. This prevents the system from remaining blocked forever. The second approach is priority assignment. When multiple agents compete for limited resources, higher priority tasks are allowed to proceed first. By establishing clear priorities, resource conflicts can be resolved more efficiently. The third approach is monitoring and intervention. A supervisory component continuously observes the system. When it detects a deadlock, it can analyze resource allocation, release locks, or reassign resources to restore progress automatically. Finally, there is escalation. Some situations cannot be resolved automatically. In these cases, the issue is escalated to a human operator or a higher-level control system, which makes the final decision and breaks the deadlock. These 4 strategies have been used successfully for decades in distributed systems and operating systems. As AI collaboration becomes more sophisticated, the same principles will play a critical role in ensuring that multiple AI agents can work together reliably without becoming permanently blocked. Another common coordination failure is the race condition. A race condition occurs when multiple agents attempt to access the same shared resource at the same time. In this example, Agent A, Agent B, and Agent C are all trying to use the same database, file, or shared resource simultaneously. If their operations overlap without proper coordination, the order of execution becomes unpredictable. As a result, one agent may overwrite another's work, updates may be lost, or the system may end up with inconsistent data. The issue is not that the agents are making incorrect decisions. Instead, they are acting independently without coordinating access to shared resources. Race conditions have long been recognized as a major challenge in distributed systems, databases, and concurrent programming. As AI systems increasingly rely on multiple agents working in parallel, preventing race conditions becomes essential for maintaining data consistency, system reliability, and trustworthy decision-making. In short, effective AI collaboration requires not only intelligent agents, but also carefully coordinated access to shared resources. Race conditions are a common challenge whenever multiple AI agents operate in parallel. Fortunately, software engineering has developed several proven techniques to prevent these conflicts. The first is mutual exclusion. Only one agent is allowed to access a shared resource at a time. Locking mechanisms, such as mutexes or distributed locks, ensure that simultaneous access cannot occur. The second approach is transactions. Instead of treating each operation separately, a sequence of actions, such as reading, processing, and writing, is executed as a single atomic unit. If every step succeeds, the transaction is committed. If something goes wrong, all changes are rolled back, keeping the data consistent. The third solution is leader election. Rather than allowing every agent to write directly, one agent is selected as the leader. All requests pass through this leader, which coordinates access and prevents conflicting updates. Technologies such as Raft and Zookeeper are built on this principle. Finally, authorization control limits who is allowed to access specific resources. Only authorized agents can perform certain operations, preventing unauthorized or conflicting actions while improving both security and fairness. Together, these four techniques, mutual exclusion, transactions, leader election, and authorization control, provide a strong foundation for reliable multi-agent systems. As AI collaboration becomes more widespread, applying these software engineering principles will be essential for building systems that are both scalable and trustworthy. As AI systems become more collaborative, another common coordination problem begins to appear: duplicate execution. This happens when multiple agents unknowingly perform the same task. In this example, 3 different agents all conduct the same research independently. Although each agent is working correctly, they are collecting the same information again and again. As a result, valuable computing resources are wasted. For large language models, this means unnecessary token consumption, repeated API calls, and duplicated processing time. These redundant executions create 3 major problems. First, operational costs increase because the same work is paid for multiple times. Second, latency increases. Instead of moving on to new tasks, agents spend time repeating work that has already been completed, slowing down the entire workflow. Third, organizations may experience missed opportunities. While AI agents are busy performing duplicate work, more valuable or time-sensitive tasks may be delayed or even ignored. As multi-agent systems continue to scale, eliminating duplicate execution becomes essential. Effective coordination ensures that knowledge is shared, completed tasks are reused, and every agent contributes unique value instead of repeating the work of others. Duplicate execution wastes computing resources, increases costs, and slows down the entire system. Fortunately, software engineering provides several effective strategies to eliminate redundant work. The first is task management. Before executing a task, the system checks whether the same task has already been submitted. If it is identified as a duplicate, the extra request is discarded, ensuring that each task is executed only once. The second solution is caching. Once a task has been completed, its result is stored in a cache. If the same request appears again, the system simply returns the cached result instead of repeating the computation. This dramatically reduces token usage, latency, and infrastructure costs. The third approach is shared memory. Multiple agents share a common memory space containing completed results and execution states. Before starting a task, an agent first checks this shared memory. If another agent has already completed the work, the existing result can be reused immediately. Finally, scheduling provides centralized coordination. A scheduler manages the task queue, detects duplicate requests, assigns priorities, and ensures that only one execution is scheduled for each unique task. Redundant requests are skipped automatically. By combining task management, caching, shared memory, and intelligent scheduling, multi-agent systems can eliminate unnecessary computation, improve efficiency, reduce operational costs, and scale reliably as the number of AI agents continues to grow. As AI agents begin working together, failures are no longer isolated. A single mistake can spread throughout the entire system. This phenomenon is known as cascading failure. It begins with an incorrect decision. An AI agent may receive incomplete information, misunderstand the context, or make an incorrect judgment. As a result, it performs the wrong action. The problem becomes much more serious when other agents trust that incorrect result. Instead of verifying it independently, they use it as the basis for their own decisions. The original error is then copied, amplified, and propagated across multiple agents. Eventually, the impact reaches the entire organization. A single incorrect decision can lead to service interruptions, inconsistent data, operational failures, financial losses, and damage to customer trust. The more connected a multi-agent system becomes, the greater the risk that one local failure will spread globally. For this reason, reliable AI coordination requires more than intelligent agents. It also requires mechanisms that detect failures early, prevent their propagation, and protect the stability of the entire system. Cascading failures can quickly turn a small local error into a system-wide problem. To prevent this, reliable multi-agent systems need protection mechanisms at every stage, from detection and prevention to recovery and verification. The first approach is fail-safe. When the system detects uncertainty, abnormal behavior, or high risk, it immediately stops the current operation and falls back to a safe default state. Rather than allowing an incorrect action to continue, the system prioritizes safety. The second technique is the circuit breaker. If the failure rate exceeds a predefined threshold, the circuit breaker blocks additional requests. This prevents the failure from spreading to other services while allowing the affected component time to recover. The third strategy is adaptive retry. Instead of retrying immediately after a failure, the system waits using an increasing back-off period combined with random jitter. This prevents large numbers of agents from retrying simultaneously and creating even more load, resulting in more stable recovery. Finally, validation agents provide an additional layer of protection. Before critical decisions are propagated to other agents, a validation agent verifies that they are correct and appropriate. Valid decisions are approved and shared, while invalid ones are rejected and replaced with safe fallback actions. By combining fail-safe design, circuit breakers, adaptive retries, and validation agents, multi-agent systems can contain failures before they spread, maintain system stability, and ensure reliable AI coordination even under unexpected conditions. As AI systems become more collaborative, technical challenges are not the only concern. Another critical issue is responsibility diffusion. This occurs when multiple people or AI agents participate in the same workflow, but no one is clearly accountable for the final outcome. Consider a typical process. It begins with planning, where responsibilities are assigned. Next comes investigation and analysis, where information is gathered. Then the solution moves to execution, followed by review and verification. At first glance, everything appears well organized. However, if ownership is not clearly defined at each stage, an important question emerges. Who is actually responsible? Each participant may assume that someone else will notice the problem or make the final decision. As a result, responses are delayed, critical issues may be overlooked, and accountability gradually disappears. In multi-agent AI systems, this problem becomes even more complex. Human operators, AI agents, automated workflows, and software services all contribute to decisions. Without clear ownership, tracing responsibility becomes increasingly difficult. Building reliable AI collaboration therefore requires more than intelligent agents. It also requires well-defined roles, clear accountability, and governance mechanisms that ensure every important decision has an identifiable owner. Responsibility diffusion can seriously weaken the reliability of a multi-agent system. To prevent this, organizations need more than technical solutions. They need clear governance and well-defined accountability. The first step is the definition of roles. Each participant, whether human or AI, should have a clearly assigned responsibility. Planners define objectives and overall strategy. Investigators collect and analyze information. Developers implement solutions. Reviewers verify quality before results are accepted. When every role is clearly defined, ownership becomes explicit. The second mechanism is an approval workflow. Important decisions should not move directly into execution. Instead, proposals are reviewed and either approved or returned for revision. This creates a structured decision-making process that reduces errors and ensures accountability before actions are taken. The third element is maintaining a decision history. Every important decision should be recorded together with its owner, the reason behind it, and the final outcome. This creates a complete audit trail. making it possible to explain how decisions were made and who was responsible. Finally, governance provides the overall framework, policies, compliance requirements, ethical guidelines, monitoring systems, and oversight mechanisms ensure that AI systems operate safely and transparently. Together, these four practices, clear role definition, approval workflows, decision history, and governance, transform responsibility from something vague into something explicit and traceable. As AI systems become increasingly autonomous and collaborative, accountability will become one of the most important foundations for trustworthy AI coordination. Software engineering has taught us that building reliable systems is not just about writing code. It is about connecting multiple engineering principles into a complete architecture. The first principle is synchronization. When information, system states, and data remain synchronized across teams and services, everyone works with the same understanding of reality. This consistency becomes the foundation for reliable collaboration. The second principle is resilience. Failures are inevitable in any complex system. Instead of trying to eliminate every failure, resilient systems are designed to continue operating through redundancy, automatic recovery, monitoring, and backup mechanisms. The third principle is distributed systems. Rather than relying on a single machine or service, modern software distributes workloads across multiple servers and components. This enables scalability, flexibility, and high availability, allowing systems to support millions of users while remaining reliable. Finally, these engineering principles naturally lead to AI collaboration. Today, software is no longer operated only by humans. AI agents, people, applications, and external services increasingly work together, sharing information and coordinating decisions to automate complex tasks. This represents the next stage in the evolution of software engineering. By combining synchronization, resilience, distributed systems, and AI collaboration, we create systems that are not only scalable and efficient, but also capable of supporting intelligent decision-making. In many ways, AI coordination engineering is the natural evolution of software engineering, extending decades of proven engineering principles into the era of collaborative AI systems. Building reliable AI systems is not only about creating intelligent models. It is about building an engineering process where people, knowledge, and technology continuously improve together. The journey begins with management. We organize teams, define responsibilities, monitor progress, and understand the overall direction of the project. Next comes task management. Large objectives are divided into manageable tasks. Priorities are established, dependencies are tracked, and execution is coordinated efficiently. The third step is knowledge sharing. Knowledge should not remain isolated within individuals or teams. Instead, it should be captured, documented, and shared so that every new project benefits from previous experience. As knowledge accumulates, we can continuously improve our capabilities. Better tools, better workflows, better skills, and better automation enable organizations to become increasingly productive over time. With stronger capabilities, organizations can make better decisions. Decisions become faster, more informed, and grounded in both data and accumulated knowledge rather than intuition alone. Finally, all of these elements enable true collaboration. Teams, AI agents, partners, and organizations work together toward shared goals while building trust across the entire system. This progression, from managing people, to managing work, sharing knowledge, improving capability, making better decisions, and ultimately collaborating, represents the foundation of collaborative engineering. And this is also the direction of AI coordination engineering, transforming software engineering into an engineering discipline centered on collaboration, knowledge, and collective intelligence. Building reliable AI systems requires more than intelligent models. It requires an architecture that enables multiple AI agents, knowledge, workflows, and governance to work together as a unified system. The first layer is AI agents. Each agent has its own role and expertise, but real value emerges when these agents collaborate toward a shared objective rather than working independently. The second layer is memory. Both short-term and long-term memory preserve context, enabling agents to learn from previous interactions and make more informed decisions over time. Next is knowledge. Knowledge from documents, databases, and previous experiences are shared across the system, allowing every agent to benefit from collective intelligence instead of repeating the same work. The fourth layer is the workflow. Workflows coordinate tasks, determine execution order, and manage dependencies so that complex activities can be completed efficiently and consistently. Above that is decision-making. Agents analyze available information, evaluate alternatives, and make decisions based on evidence rather than isolated assumptions. Finally, the entire architecture is governed by governance. Policies, accountability, monitoring, and oversight ensure that AI systems remain trustworthy, transparent, and aligned with organizational goals. When these 6 layers, agents, memory, knowledge, workflow, decision-making, and governance, are integrated, AI becomes far more than a collection of independent agents. It becomes a coordinated, scalable, and reliable collaboration platform capable of supporting organizations in solving complex real-world problems. This layered architecture forms one of the central foundations of AI coordination engineering. Throughout this presentation, we have explored how AI systems become more reliable, scalable, and trustworthy through coordination. But ultimately, AI coordination engineering is about much more than technology. It is about creating a better future. The first step is to build better AI. By combining high-quality data, reliable algorithms, robust infrastructure, and human values, we can develop AI systems that people truly trust. The next step is to enable better collaboration. Rather than replacing people, AI should work alongside humans, combining complementary strengths to achieve better outcomes. This collaboration leads to better organizations. Organizations become more adaptive, productive, and innovative because people and AI can coordinate effectively. From there, AI can contribute to a better society. By emphasizing fairness, transparency, accountability, and safety, AI can create positive social impact while earning public trust. Ultimately, AI coordination engineering is a framework for connecting AI, people, organizations, and society into a single collaborative ecosystem. The destination is not simply more intelligent machines. It is a future where intelligence is coordinated, trusted, and shared. In the final slide, I'd like to briefly introduce the open research initiative that supports this vision. Before we conclude, I'd like to introduce Chinoba.org. Chinoba is a nonprofit, open research initiative dedicated to advancing AI collaboration. Our goal is to connect AI, people, organizations, and society to build trustworthy, collaborative AI systems that create long-term value. Our activities are built around 4 pillars. First, research. We explore the theories, architectures, and engineering principles behind AI collaboration and multi-agent systems. Second, practice. We apply these ideas to real-world projects, transforming research into practical solutions. Third, sharing. Through publications, books, seminars, videos, and open educational resources, we make knowledge accessible to everyone. And finally, connection. We collaborate with researchers, engineers, educators, and organizations around the world to build an open community dedicated to responsible AI. Our vision is simple. We believe AI should be trusted, grow together with people, and contribute to a sustainable future. We also believe that the next generation of AI is not only about larger models or greater computational power. It is about better coordination, better governance, and better collaboration. If today's presentation has inspired you, I invite you to visit Chinoba.org, where you can explore our research, articles, books, open source projects, and educational resources. Thank you very much for your time and attention. I hope this presentation has provided new perspectives on the future of AI coordination engineering. Thank you.